Chapter 9. And God made two great lights, the greater light to rule the day, and the lesser light to rule the night. The purpose of this chapter is to explain that God used natural laws to organize the solar system. The organization is demonstrated by the predictable nature of the solar system, specifically the organized geological structure of the Earth and the other planets. However, I have heard some who believe the Earth was brought into our solar system from somewhere else. I believe the Earth was created along with the other planets where they are. The Earth's unique ability to support life is because of the Earth's constitution, position in space, and abundance of water. The solar system, the nebular model. A star created out of a molecular cloud was discussed in the previous chapter. Now let's take this a step further and explain how a system could form from a cloud. Imagine a large molecular cloud of gas and dust that begins to collapse. The particles randomly gravitated towards the cloud center, creating both heat and a general rotating motion. There were areas of lesser and greater concentration where the other particles would attract. The more the cloud collapsed, the faster it rotated. The faster it rotated, the more flattened it became. Most of the mass was collected at the center of the cloud, and eventually the protosun was formed. The remaining matter is flung into a broad, flattened disk from which the planets later formed. Planetary accretion. Materials heated up and began to stick together throughout the cloud. At the outer perimeter, initially ices and, for a short period, rocky materials condensed, forming bodies of rock and ice. This explains why the gas giants, Jupiter, Saturn, Uranus, and Neptune, are in their location and what they are made of. Closer to the center of the cloud, where temperatures were higher, ice, rocky materials, and finally metals condensed. These form rocky and metallic bodies which have gases locked up with them. That explains the consistencies of the inner rocky planets of Mercury, Venus, Earth, Mars, and the asteroids. Atoms joined with atoms, becoming molecules. Molecules joined with molecules to form rocks. Small rocks combine with other rocks to form very large rocks. And huge rocks combine with others to form planetesimals, which are like building blocks of planets. The planetesimals continue growing by accreting any matter coming within their gravitational influence and, like a vacuum, sweeping up everything in their path. Eventually, one body dominated an area of the cloud. These were the protoplanets. The protoplanets continue to grow by accretion as they pass through the cloud. Perhaps by then, some protoplanets had acquired a primitive atmosphere of a sort. As the protoplanets were growing by accretion, the protosun was heating up. Its nuclear furnaces were lit when the protosun became hot enough to fuse hydrogen. It blew off its nuclear cocoon along with all gas and dust, which was not gravitationally bound from the inner part of the solar system. That left the smaller planets with little to no atmospheres, while their outer planets were far enough to retain their atmospheres, or even to collect the gas and dust from the inner part of the solar system. What should have remained would be a sun, orbited by many planets. The planets should orbit the sun elliptically within the same plane. The planets' composition should reflect the composition of the area of the nebular cloud from which they were formed. The inner planets should be metallic and rocky, having some gases and ice, and the outer planets should be composed of rocks and ice and should contain more gas. Differentiation. Earlier I mentioned that ice and gases were tied up with the rocks which form the Earth. When rocks become molten, they release the trapped gases. The gases then rose because they were lighter than the surrounding material. The process of lighter materials rising to the top is called differentiation. Through the process of differentiation, in the inner rocky planets, three important gases necessarily for life were released from the rocks: nitrogen, carbon dioxide, and water vapor. Earth, a comparison with our two neighbors, Venus and Mars. Interestingly, the Earth can support life while its neighbor planets do not. According to the nebular model, planets in close proximity were created out of the same area of the cloud and should have similar compositions. This means the Earth, Venus and Mars should have water. So why don't Venus and Mars have water like Earth does? It will be shown that there was and still is water on Venus and Mars. However, size and proximity to the Sun have eliminated almost all water from our neighbors, though we were created out of the same part of the molecular cloud. Atmospheric pressure and temperature. Two things permit water to flow: pressure and temperature. Water turns to ice at 1 pressure atmosphere and 0 degrees Celsius. Water becomes a vapor at 1 atmosphere of pressure and at 100 degrees Celsius. Between the two temperatures, water flows as a liquid. To illustrate the importance of how pressure and temperature affect a material, let's look at dry ice, frozen carbon dioxide. A block of ice left in the sun would melt, forming a puddle, eventually evaporating. But no puddle would form if you left a block of dry ice in the sun. Instead of melting, thick blankets of gaseous carbon dioxide clouds would waft away in the breeze and instantly go from a solid to a gas. The reason dry ice acts this way is the lack of pressure. The Earth has sufficient pressure to hold carbon dioxide together in a liquid form, but has sufficient pressure to hold water together in all three states: gas, liquid, and solid. The Earth's temperature is determined by its distance from the Sun, rotational speed, mass, and atmosphere. The Earth is able to hold on to its atmosphere because of its mass. Only the lightest gases like hydrogen easily escape from this planet, but heavy gases such as oxygen can't escape. The heavier gases remain here to help moderate the surface temperature and increase the atmospheric pressure. Photodissociation. Photodissociation is a process whereby photons tear a molecule apart. Here we will discuss the photodissociation of water by ultraviolet rays. UV rays break the bonds between oxygen and hydrogen molecules. On Earth, hydrogen easily escapes into space, while oxygen remains gravitationally bound on the planet. Water as a gas is extremely vulnerable to photodissociation. Venus and Mars, what happened to the water? Venus. Venus has almost the same mass as Earth, so it was able to retain its atmosphere. Venus is covered with dense blankets of clouds and has a crushing atmospheric pressure. Only very slight traces of water vapor have been detected, however. So where did the water go? Venus is hot. It is hotter than the Earth for two main reasons. First of all, it is much closer to the Sun. Second, its dense cloud cover traps virtually all the heat, making the planet's surface a veritable hell, with temperatures hotter than a kitchen oven. At such high temperatures, water could only exist as a gas, and as a gas, it would be vulnerable to photodissociation. Venus probably lost its water a long time ago through the process of photodissociation. Mars. Mars has about half the mass of Earth, which means it has a lot more trouble holding on to its atmosphere. Mars is also further away from the Sun than the Earth is, so it receives less of the Sun's radiation. There is ample evidence of running water on Mars in the past, but that is not the case today. Most of the water detected on Mars today is in the form of ice. We know there is water on Mars because it has been detected in the polar ice caps, which are believed to be composed of both water and frozen carbon dioxide. Initially, when Mars began to differentiate, it held on to some of its water. There must have been enough atmospheric pressure on Mars in its beginning to allow water to flow. This means there must have been clouds, condensation, rain, rivers, and possibly lakes. But those days are gone along with the flowing water. So what happened to the water? Mars is small, which means it has a difficulty holding on to its atmosphere. The lack of atmospheric pressure forced water into a gaseous state, and UV ray tore the water molecules apart. The hydrogen easily slipped into space and left the heavier oxygen behind to combine with the minerals on the planet. The oxidation of iron on Mars gave the planet a rusty hue. Mars lost virtually its entire atmosphere and has a negligible amount of atmospheric pressure. Under these conditions, water could not exist as a liquid. If ice tried to melt at the edge of a polar ice cap on Mars, it would instantly vaporize. Photodissociation would take care of the rest. Conclusion. The solar system follows an organized pattern. The Earth, the Sun, and all the other planets in our solar system were formed out of the same nebula cloud. The planets follow a mathematical sequence called the Taddeus-Bode law. This law tries to explain the distances each planet is from the Sun mathematically, and might be more of a mathematical curiosity, but it is something to consider. The composition of the planets also reflects the composition of the area of the cloud from which they were organized. The heavier elements form the inner planets, while the more gaseous regions form the gas giants further out. And, for various reasons, the Earth held on to its water, while its neighboring planets, Venus and Mars, did not.